back, and now we will have Mark Burgess. He's our last speaker in the morning session at room 104. Mark is a PhD student at the Australian National University. He's studying distributed algorithms for the control of electricity microgrids, and he has worked for several years programming in Python at Repository Power, I think, and he's also a member of a community called Make Hackervoid, and now we will hear his talk on linear genetic programming in Python bytecode.
Can everyone hear me? All right, hello everyone. My name is Mark. I'm a PhD student and I'm excited to talk today about linear genetic programming in Python bytecode. Yeah! All right, it's a bit of a mouthful. So I don't know, I'm a cool guy, and this is something I feel like is kind of pretty cool in a way, so I thought I'd show up today and kind of imbue my nuggets of wisdom. You know, the kind of little ideas that you can kind of take away and maybe they kind of grow in your mind and you thought, maybe I might try this as like a little side project somewhere. So I don't know, we'll start where we go. So the first thing I want to know, right, I need this audience feedback. I need to pitch it appropriate to you guys. So what I want everyone to do is I want everyone to raise their hands. Everyone raise their hands. All right, okay, just one hand will do. All right, now when I say the words genetic programming, that phrase, I want you to put your hand down if you barely know what that means. If you've got some semblance of an idea what that means, keep your hand up. All right, hands down or up. Okay, we're pretty good, All right, okay. Now for those people that raised their hands, right, I want to know how many people have actually done genetic programming. All right, so raise your hand up if you've actually done this thing.
Does unicorns count? Or has it...
Sorry?
Does it have to be in the wild or does a unicorn count?
Anything, yep. If you've done anything that resembles it, hand up. All right, cool. All right, next question. And this is an important one. Who has ever done anything or fiddled around with Python-y bytecode? Okay, yeah. All right, fair enough. I like that. All right, so the first thing I'm going to do is I'm going to skip through the first little introductory bit because I did that. And I'll talk very briefly about it, what it means for something to evolve. Because what genetic programming is the evolution of computer programs themselves, right? So the idea is that there are central components to what would something broadly be considered to be evolution. There's an initial population of things, right? Now this can be organisms, bacteria, spanners, or in this case, programmings, right? So we start with an initial population. There is some evaluative measure, in effect or actual, between organisms, spanners, or programs, right? So that evaluation to some degree, in effect or otherwise, actually assigns to each of them what is generally called a fitness, right? Which, more often than not, is actually a function, conceptually or otherwise. Thence there is a selective step, so, you know, like evolution by natural selection. This is the analog. We actually select the best programs, spanners, designs of websites to actually make it into the next generation. Thenceforth, from a selective step, we have, I would call, variation. So if we're talking in a biological sense, this is mutation or crossover of genes or whatever have you, right? This is like that little extra degree of randomness. And thence that forms the next generation, where if we reevaluate, select, vary, reevaluate, select, vary, and this iterative procedure continues until such a point as we reach a terminating condition where we say, okay, we've got a thing, a spanner, that we're happy enough with to say that that is the result of the evolution. So that is like in the broadest kind of sense, like kind of central elements to what it means for something to evolve, right? So in the case of genetic programming, when we're evolving programs, it's a little bit like a juggle kind of thing. There's a lot of factors to consider, and there's those stages broadly considered that we need to implement. So the first thing we need to do is when we're programming programs and the evolution of programs in a computer, to some extent we need to choose what is called the representation of that program. So, like, I think evolutionary genetic programming has been loosely around since like mid-late 80s. It's kind of developed particularly by a guy named Koza. But this was kind of like the original representation of programs, so as trees. So if anybody here is familiar with Lisp, this is kind of more or less almost Lisp-style syntax, right? So we've got like just generic tree. That is a program. Now, there are other representations as well. So for instance, this is a tree representation. The other thing we can do is we can just go like choose just individual instructions, which to some extent I'm sure we're all moderately familiar. So opcodes. So for instance, this is just Python opcodes, which we'll come back to later in the speech when I get down to it. But there's other opcodes we can choose. So we can just go straight to x86 if we want, or we can choose our own instruction set that's just linear in execution, and linear executed evolution of programs is called linear genetic programming, funnily enough. But there are other representations too, and we need to keep these there open. So the top one there, if you're familiar with it, is called brainfuck. Right? We can evolve brainfuck if we want. It's not a particularly good representation, but we can do it. And there are tutorials online on the evolution of brainfuck. On the bottom left there, we've got what is the definition of a grammar. Right? So it's kind of familiar to EBMF notation or whatever. And there's actually grammatical evolution is its own kind of thing. It's definitively, it's a real thing. And if you want to go down that thing, there's research and papers and all kinds of stuff on that. On the right there, we've got an esoteric language that I pulled from the interwebs called beeswax, which, hands up here who has ever heard of a funge? Befunge. Wow, that's terrible. Okay. So it's like brainfuck, except it's composed of more letters, and it's kind of like you execute across, and then it hits a character, and then it executes downwards, and then to the. It's an esoteric language. That's what it's called. But you can evolve whatever you like. All right, you just need to choose a representation, and you can evolve it. Right now, important part. Like this is the choosing of the representation of your programs, insofar as you want to do the evolution of programs, is really quite important. Because whatever representation you choose actually defines the space where the evolution can actually take place. Right? Now, it's kind of important because there's this thing called the curse of dimensionality, which means that if you fire too widely, and if you choose a programming space that's too big, it'll take just that much more longer for the computer to converge to something that you might like. So if you can choose a very constrained language, right, you need to make sure that it satisfies the sufficiency condition, that is that you can actually evolve something that looks like what you want using that language. But if you choose more constrained, you actually get generally better results. So in kind of making these things that evolve, right, there's kind of broad conditions. You need to make sure that they don't crash your computer, right? If they can crash your computer, it's probably bad. The other thing is you kind of need to make sure that they're relatively type consistent. So you're not multiplying floats by bools, you know, or, you know, ints by objects, because what sense does that make? But the idea is that once we've got in our heads this evolution, there's programs, and we've got a representation in which this space in which we can evolve programs, right? The next stage of the game is to make an initial population of these programs. Right? Now, broadly speaking, depending on how you represent it, there are different algorithms to go about it. So for instance, the oldest method is to generate programs of trees. And there's actually definitive, like, there's ramped and half, and then there's half ramped and half, and like there's different actual algorithms used to design random trees that contain the most features. They're the most random. But depending on how you represent your programs, depends on the algorithms you might like to initialize your population with. You can also seed the population with something that you know is okay. The central part of evolution is that you want to keep some degree of variety in your population, right? So if you just start with all one program, it's probably not the best start that you could probably do. The next stage is to define, to some extent, an evaluation over your programs in the population, right? So traditionally, this has kind of like been called a fitness function, right? Where you more or less evaluate the output of your program to what you want, and then you just assign it a number to some extent based upon that. It's actually a lot, you know, there's a relative amount of finesse in choosing an appropriate fitness function. So probably the most important of that is that your fitness function is smooth. So that's, to some extent, that means that as much as is possible, you want the actual numeric value that is the output of your fitness function to change small with regards to a small variation in its input program. It's an idealization, And we'll come to why you might like that later. The next part is the selection. So we're modeling evolution. There's the natural selection part. And it's in the kind of programming you want it more or less to generally select the fitter individuals, but not exactly. If you only select the best individual of your population, right, then you only just end up with a population of one kind of individual, which is kind of like, you know, variety goes down to the sink. So there's actually different techniques to select generally what is the better kind of half of the population. So there's tournament, you know, you just select 3 individuals and then you compete them to see which one's the best, and then that one survives to the next population. There's another one called roulette, which is basically you select a program in proportion to its assigned fitness value. All these work. So a lot of the selection kind of process, you need to evaluate your programs, and you want it to some degree to keep the diversity. So your selection can't be greedy, as it were. The next stage, because we're doing evolution here, is you need to put in to some extent a little bit of that mutation factor. So obviously, depending on how your programs are represented, depends upon how you can readily introduce that mutation. So for linear programs, you can do duplication, inversion, deletion, insertion, translocation. Anything you can do, you can mix and match, you can just randomize the whole string. So, you know, it's kind of like up to creativity to some extent, what kind of mutations and variations you want to put in this thing. With the case of tree-based genetic programs, a lot of the operations just consisting of swapping, changing, and generating random subtrees is an example of variation. And putting it all together, what the idea is that we have this kind of like with initial population that's randomly generated with an assigned fitness value, and it's kind of like little variations, selection, and it's kind of like gradually over time we want to get this like individual with high fitness value to cross the finish line, which is our terminating condition, at which point we say, we've just discovered a brand new algorithm for doing whatever we want. But yeah. Now, I suppose genetic programming is one of those things where like it's exciting in a way, because what you're doing is you're throwing the problem to a computer to say, do the programming for me, in a sense. Now, there's a lot of finesse to it, and it's kind of, maybe I've just like shotgunned you, right, the concepts. So what we're going to do is we're going to go slowly through an example of this thing, right? Now this example is called Symbolic Regression, and it's taken directly from a field guide to genetic programming, which is a Creative Commons book, one of my more favorites. You can get a hard copy for about $10. So what we're going to do, this thing called Symbolic Regression, is where basically you have a series of data points and you fit a function to it. Now the function is actually defined symbolically, so any function that you can define by a combination of symbols, it'll fit to it. All right, so what we want to do in this example is we've got a series of data points over the range -1 to 1 that actually just coincidentally is directly on the function x squared plus x plus 1. And we're going to actually evolve symbolic expressions that converge, hopefully, to the ideal value of x squared plus x plus 1, right? So in principle, if you've got like a scientist and in nature and you're collecting data points and you say, oh, I just want to fit a symbolic expression to those data points, it's like throw it to a computer, done. Though it's often not so neat. All right, so we've got x squared plus x plus 1 over the range -1 to 1, including the operations of plus, minus, multiplication, and protected divide. So if you divide by 0, it ordinarily throws a div by 0 error. So protected divide is just where it returns a 0 if you divide by 0. It's just a safeguard. And the measure of fitness is going to be the sum of the absolute errors over the interval -1 to 1 with 0.1 increments. We're going to generate an initial population via technique rampant half and half. We're going to have a population size of 4, which generally speaking is tiny. And we're going to terminate when we have an individual with a fitness less than 0.1. All right. So the first step is if we have randomized an initial population. So we've got 4 programs, just randomly generated trees that correspond to symbolic expressions. So we've got x plus 1, x squared plus 1, 2, and x. All right. And those are our initial population of programs. Well, mathematical expressions of programs to some extent. And then now what we're going to do is the next step of the thing is to evaluate those programs. So, next slide is the evaluation of those programs with respect to our desired ideal fitness function. So in the black there's x squared plus x plus 1. And the red dotted line is the actual graph of that, of each expression over that same domain x minus 1 to 1. So in the case of, we got A, B, C, and D, with the fitness values A, B, C, and D, 7.7, 11, 17, and 28. So A is closer to x squared plus x plus 1 than is D. That's what that means. It's got a smaller fitness function in this case. So those 4 correspond to those 4. All right? Everyone with me? All right. Now, what happens is we have an initial population, right, of those programs, and we've each assigned to those programs a fitness function, right, values of those fitness. And now what happens is we need to apply the selection. So of those 4 programs, it so happens that A is the best. It's got the lowest fitness value, which in this case is good. And so by our randomness, we just say, okay, our selection process just selects the best individual and carries that into the next generation. So boom, top generation, second generation. All right, so A just goes straight reproduction, and we can set a parameter of probability for that if we like. All right, the next thing that we want to do, so you know, this engine kicks in and selects randomly, to some extent, a individual C, which is not the best, it's not the worst, it's somewhere in between, because we do want to keep a little bit of randomness about it, and it introduces a mutation. So it chooses a random node, which just so happens to be 2, and generates a random subtree and just poof, inserts. All right, so we end up getting this function down here, which just so happens to coincide with the value 1. So the next thing happens is, all right, well, let's do another thing. So introduce an operation called subtree crossover. Right, so in this kind of machine thing that we're kind of imagining of selection and variation, it randomly selects, coincidentally, the best 2 individuals, because it selects based upon the fitness value. And what it does is it chooses 2 branches and it crosses them over. Right? So we've got the plus and the x, and those subtrees literally cross over at that point. So minus x minus 0 gives you x, and then that there corresponds to 1 plus x plus 1 times x, producing the last individual. Now this goes from our first generation, and apply all these operations with stochastic probabilities, gives you our second generation. And the idea being is that through this thing, we're hoping that the second generation will be closer to our ideal outcome. And coincidentally, in this example, we end up with the best possible individual, x squared plus x plus 1. Now this is just like a little sandbox example, and ideal solutions rarely come about in nature. But you know, hey, why not? Just illustrative point. So in this kind of a way, what we've done is we've started with a problem that we want to evolve a symbolic expression that corresponds to a program that evaluates as close to x squared plus 1 x plus 1 as possible. We've thrown it into the algorithm, and out comes what is the solution to our thing, which is a program. All right. I want to introduce just like rather than just hand wavy talk about these trees, right? There's a little Python package which I like called DEAP. It's kind of a framework in which you can download this thing, you can import DEAP, and you can actually play with this. And it has kind of more or less inside of it many of the operations that you would otherwise have to code by hand if you were to do it by hand. So a lot of languages have packages to do this kind of genetic programming. So you know, Java and C, and this is predominantly Python's one. And it's actually a pretty nice little package. So I just kind of want to introduce like a little example on how to use this thing before kind of going on to the Python bytecode stuff. All right, so this here is a really basic example on how we do, well, this is genetic algorithms, but similar. So it's kind of more or less composed of kind of more or less 2 different parts. Well, technically 3. So it's kind of a little I always hate frameworks because to some extent there's that initial learning curve before you actually get good at it, and it feels like you're doing the hard thing first, which being lazy I don't like. So there's 2 things there. It's got creator and toolbox, right? So toolbox is relatively easy to just straightforward out and out with it. What it is, it's kind of operates like the partial function, you know, so from functools import partial. So what happens is, so for instance, toolbox.register, and we've got a name, attr bool, and we say, okay, we're going to make a function that's called attr_bool, and it's going to be the function random.randint, which I'm sure we're familiar with, the parameters overrided of 0 and 1. And inside the DEAP toolbox, it's just got literally self.attr_bool equals partial random.randint parameters 0, 1. Right, no frills. The other one is we've got the creator in the DEAP toolbox, which basically is kind of the same thing for classes. So what happens is when we go, so creator.create individual, and then you give it a class, array.array, and then you give it keyword overrides. So what it does is it literally goes, so the namespace inside the creator creates a class called individual, which is an instance of the array class with an overrided constructor setting the values of type code to be in fitness equals blah, blah, blah. So it's kind of a general purpose tool. And so what you do in this framework is you literally creator.create your classes, so your individual, and then create toolbox.register functions. So you register mutate, select, evaluate, mate. And then what happens is you basically pass it over to one of the algorithms inside the DEAP toolbox and you just go solve. So in this case, we've got EA simple, and we just supply the parameters that we want. So the crossover probability, the mutation probability, the number of generations, and we've got a Hall of Fame to collect the best individual over them all. And then we print the top individual, Hall of Fame index 0. All right. So basically that one there just is it's a population of arrays that consist of bytes 0 and 1, the fitness evaluated to be the sum of those bytes. So what will happen is over time, and we can run this program if you want, it'll just evolve 1, 1, 1, 1, 1, 1, 1 at the end of the generations. So that's an example use of DEAP. And we notice that in this, we're kind of using some of their inbuilt functions. So we've got mutation flip bit with a probability of 0.05. So what it does is it just scans through the thing, and based on that probability, it just flips the bit between the 0 and 1. And that's an inbuilt thing in the toolbox that you can just plug and play. So it's nice. So like that's really quite nice. But the tree kind of representation with tree traversals and subtree crossovers and mutations generating random trees and the registration of all the different types of functions that you can put in your tree is a lot more work. So DEAP has got you covered, and what it's done is it's kind of more or less, it's done the hard yards for you. So you can just say, all right, I want a set of little nodes in the trees. So the set of nodes in the trees is called the primitive set. And so I want the operator.add as one of the nodes in my trees that the program can evolve. So we say primitive set.add primitive, and then we operator.add, which is just the plus operation, and we say it's got arity of 2, which means it just takes 2 things. So it's not particularly complicated. So add primitive operator.negative with a parameter of 1 input. All right. There's this thing called an ephemeral constraint, which is basically, so in that case, it generates a random number between -1 and 1 created on the creation of a tree. It's a bit of a, yeah. And we create the individuals, which are consisting of the trees. We say, all right, we want a population to be ramped half and half trees. We just more plug and play. We want, now I suppose that thing that we want here is what we're doing is we're doing symbolic expression. So evaluate our created function over the range -10 to 10. So sorry, -1 to 1, which is divided by 10. And we've defined for ourselves an evaluate expression. So that's probably the most complicated part, which is kind of more or less defining the fitness function for our trees. So in this case, it's just returning the sum squared errors in comparison with x to the power of 4 minus x to the power of 3 minus x to the power of 1 minus x. So it's kind of what we did before in our conceptual example, but this is actually in DEAP, using the framework. And, plugging and playing is nice, so why not use it? Now, I suppose one of the things that, I find trees a little bit ugly, because traversing and using trees, when you program it out, tends to involve a lot of recursive functions. And my mind I just how do I write a recursive function again? Right, that's right. But the thing is that when you're actually using these things, and when it comes to an execution of the tree to evaluate it, what happens is the Python algorithm actually has to go through, maps and parsers and all this kind of thing. But this is kind of a little portion of the DEAP package code that's actually kind of inspired. I think it's from SymPy. So if anybody's used Symbolic Python here. Where what it does is actually, when it compiles and evaluates one of these trees, what it does is it actually converts the tree into a string, right? Actually formats that into a Python lambda code string, and then calls eval on that. So if you know anything, it converts it to that Python string, and then it rehydrates that into an abstract syntax tree thing, and then it flattens that back again into bytecode, and then it runs that, which is a little bit ugly. I was reading, in motivation for this talk, I was actually just browsing around the internet and thinking, whoa, let's come up with something interesting. And there was an example of a guy that he said, all right, this is crap. Maybe we can do better. So it's like, let's evolve Python bytecode directly. Right? It's kind of like, oh my God. Anyway, we've got 5 minutes left. Shit. All right, I was only just beginning to get to it. All right. So Python bytecode is one of those things that kind of like, it's kind of scary in a way because to some extent, some parts of it are just undocumented. So you don't find nice big tutorials on this is what that means, this is what the other means, and let's put it all together nicely. So there's really kind of, I want to give you like the tools so that you can go and fiddle, right? So I'm just going to minimize this thing here. Oop, no. We're going to load up a little Python shell. So going to go Python 3. All right, everybody reading? All right, so what we're going to do is we're going to define a function. Let's make something up that's a bit garbage. When I can spell. All right, so we've just defined a function A. Now we can look inside A, we go dir A, and we get a whole lot of stuff, and it's a bit scary. But what we do is we can actually type A, and we notice that we've got a class function. Whew. Now if we like, we can actually instantiate a class function. So we go, so we're creating, we can actually create functions using constructors. It's freaky, right? So we've got this thing called a code, and we've got a dictionary of the globals. Now, it's kind of like, we understand that there's a global dic and the rest are optional, but there's a thing called the code object. So we can actually access the function's code object by going a.code. We've got, ooh, it's a code object, right? Now, we can look inside the code. We know there's a lot of stuff, but none of that's important. So what we can do is we can go type a dot, and we've got a code class, which we can instantiate directly. So in defining a function, we need to supply a code class, which we can create also by instructors. Now, all of this here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different little pieces of information that go into creating what is the code object that is essentially the encapsulation of the bytecode that goes into the Python virtual machine and executes all its doodah. Now, I think we're fairly up for time, aren't we? 2 minutes. All right, I'm just going to hand it over to questions. But thank you. All right.
Thank
Anyone?
Can you see the code string?
What's that?
Can you see the code string?
For what? Yeah, sure. You can. Yeah, okay. So we can go a dot code dot dot, and it's where is it? Code. That's the code string. It's pretty small. So actually that corresponds to, what is it? It's like load argument 1, add and return. Like load argument 1, load argument 2, and add and return. Yeah.
Thanks for the talk. Is this model of evolving functions actually useful? So does it give us expressions that otherwise are harder to get? Or like, is there a legitimate benefit to this?
Absolutely. Okay, so genetic algorithms, right, the process of evolving programs. So it's pretty difficult to say that a computer can be better at what you do than you do. Like that's not on the horizon just yet. But what it kind of can do is, to some extent, it can kind of come up with things that, if they're small and concise, can be difficult to achieve otherwise. So one of the things that evolutionary genetic programming has been used very successfully to do, for instance, is to evolve electronic circuits, as an example. So like I think there's a competition called the Humes competition, to use genetic programming to come up with actual novel designs of circuits that either reinvent, that either are completely novel and useful, or are actually reinventions of human inventions of particular circuits. So genetic programming can kind of come up with rather surprising results that you might not otherwise have get, and sometimes those can be difficult to attain. Any other questions? Go for it.
Thank you. Great talk.
Thanks.
Just going back to when you were on looking at DEAP, and you were adding the operators as nodes in your evolutionary tree.
Yep.
I was just wondering, how do you do loops? Does DEAP have a clean way of doing this, or do you have to define functions that map or act on arrays?
Good question. So like when we're doing programming as humans, one of the things that we do a lot of is looping. Right? It's just like one of those basic elements that we do and include. So including looping in our evolution, right, there's this really common pitfall of accidentally evolving an infinite loop and then hanging in the computer. Right? I mean, hey, if it can evolve, it'll happen. It's like Murphy's Law. So with, depending on how you represent it, you can include loops quite readily, but there's a little bit of a kind of like a creativity of problem. So, you can obviously include looping, but constrain it such that there is literally a maximum iterations that the same loop can actually go through before it just falls out and goes to the next line. There's other things, so you can actually set, like I read of people who do, like they literally set that the maximum execution time of a given program is X, and if it goes over X, then we presume it's got an infinite loop in it, and we assign it like -10 fitness, is an example of getting around that and having total flexibility in the structure. So, if your tree consists of operations on arrays, right, you can include an operation that is like a least comprehension of that array, and obviously that's closed, and it's not going to fall in that infinite loop trap. But yeah, there's lots of creative freedoms with regards to genetic programming.
Okay, thank you for that talk, Mark. You ran out of time for questions.
All right.
And here you have your Mark.
Thank you.
Yeah, thank you very much.
Cool.
Okay, lunch.